Remember that our theorem regarding the convergence of a geometric series requires that we start at the 0th term, right? So our first term is at k equals 0. So the question then arises, what happens if we don't start there? And that's what this page is going to kind of establish for us. How does it change? So let's look at the first part, which should be very easy because that one actually does start at 0. So let me just remind us all real quick. So if I have k equals 0 to infinity of a times r to the k, that would be a over 1 minus r, as long as the absolute value of r is less than 1. If it's greater than or equal to 1, then it diverges and it's not anything. Okay, so if I look here, I've got 0 as my starter, and then a is hidden. So there's an a in there, and it's 1, because we don't see a number in there, so it's 1 times. If it was 0, then there wouldn't be anything, because 0 times anything is 0. So it has to be 1, because 1 times a half times a half times a half will work out. And then r is a half. You'll notice that the absolute value of r is less than 1, which is great. It means it converges. Wonderful. Okay, so that means that I know that this will follow that formula. And so it will be a over 1 minus r. So this series right here is a, which is 1, over 1, take away r, which is a half. So that would be the same as 1 over a half, which is 2. No problem, right? Follows that theorem beautifully, right? So this is the theorem that we were following, which in our book was 10.7. All right, so now what we want to ask is, what happens if we don't start at 1? What happens if we start at 4? See right there? Sorry, I'm having problems with my highlighter. Okay, now let's think about that for a second. So that would be the same as starting at 0 but then subtracting away from the 0 to the third term. Because if we stop at 3, let me write this out. Right. This would be all of the terms, 0, 1, 2, 3, 4, 5, so on, right? And this one will get rid of 0, 1, 2, and 3, which means that I'll have 4 and beyond left over, right? So if this one goes from 0 to 1 to 2 to 3 to 4 to 5 to 6, and this one goes from 0 to 3, if I take 0 through 3 away from this one, then that would give me 4 as my starter. Clever, huh? So let me just make a note. Right? Not stopping at 4, we stop at 3 in order to make it so that 4 is what's left over. Okay, well, this one over here, we know what this is. I'm just debating my color choices here, sorry. So we know that this one from part A follows the formula. It's 2. Right, we know what it is. We found it right there. It's 2. But then we're going to subtract away, right, minus, and then we have to think about what all these other ones would be. So this bit right here, what would that work out to? So let's put in 0, 1, 2, and 3 in our heads. So let's start at n equals 0. So if you put 0 in here, a half to the 0 would be 1. Plus, because it's a sum, so we would add. Now let's put 1 in. Well, 1 would be a half to the 1, which is a half. Plus, now let's put in 2. A half to the 2 is 1 to the 2, which is 1, over 2 to the 2, which is 4, plus, last one, 3, which would be 1 over 2 to the 3, which is 1 over 8. Right? So we've made an adjustment for the fact that we're starting at 4. So since we're starting at 4 instead of starting at 0, this is what we're doing. So this would be 2 still, And then this we could find with a calculator, with Desmos, with whatever. And let me pull that up 1 second. All right, so let me pull Desmos here. So that's 1 plus a half plus, oop, got an error out of that, plus 1/4 plus 1/8. So it's 1.875. If I want it as a fraction, I can click the little fraction button and it tells me it's 15/8. So 15/8, aka 1.78, excuse me, 1.875. Either way. Okay, so if I go back to my document camera so you can see. So this is 15/8 or 1.875, either one. So I'll do the fraction, because the fraction's harder. So if I do 15/8, so this is 16/8, take away 15/8, which would be 1/8, or 0.125. So think about what we're doing. We're making an adjustment right here. This bit right here is an adjustment from the 2, right? So 2 is the sum when it starts at 0. So we're making an adjustment for starting at 4 instead of 2. Right? So because we're starting at 4 and we adjusted, this is what we get. Now, that adjustment that we're making is basically that we're subtracting something called the nth partial sum. So we're taking away, in this case, well, the 4th partial sum, because 1st, 2nd, 3rd, 4th. The numbering's always off by 1 in terms of number for the ordinal number that we say. So we say 1st, but we mean 0th, right? N equals 0, and then 2nd for n equals 1, and so on. So what we did was we subtracted away S4, the partial sum of the first 4. Now let me prove it to you. So according to this, there's a formula for that partial sum, because you can imagine, I mean, we did it here for 4, but for 9, it would get really annoying. It would get tedious. So they came up with a formula for that nth partial sum. And I'm going to prove to you that it works right here, because this is the same problem we just did. So it's starting at 4 right here. So if we take this and we say, okay, well, that's the full series. Oops, sorry, n or k, it doesn't matter. So if I say n equals 0 to infinity, and I say a half to the n, right, that's the full one. That'll be the 2 right here. But then I subtract away, instead of writing this out like this, suppose I say that's the 1st, 2nd, 3rd, 4th partial sum. So I'm going to subtract away S4. According to this, I should be able to use this formula to figure this out, rather than having to write all these out and add them all up. Because writing them out and adding them up was fine for 4, but again, for 9 or 10, it's going to get tedious. So we would like a formula to make it work for us. So let me prove to you that this formula will work. All right, so we already know, no problem, this part by A is 2. Like, we already learned that. Oop, I'm not making my arrow go far enough over. There it is. So we knew that, no problem, no question. It's the formula, ta-da. So my challenge is to show that this bit right here is the same as what we came up with up here with the 15/8. So A, remember, is still 1. It's right there. A is still 1. R is still a half, right? Right? That part hasn't changed. So I'm going to use that in the formula. So A, which is 1, times 1 minus, and then I'm going to take r to the n, which in my case is 4, right, over 1 minus r. So I'm going to take a half and a half. All right, so let's go use Desmos and prove that this is the case. So let me grab my Desmos. Okay, so I'm going to type in that formula. So it's 1 times, which the 1 times was not really necessary, but whatever. All right, I'm going to take 1 minus 1/2 to the, now it's not n, it's 4 for us, right? There we go. Over 1 minus 1/2. Ta-da! It's 15/8. They're the same, right? This addition right here and this formula right here get us the same partial sum, which is S4. It's the first 4 terms of that series, which again starts at 0 and ends at 3. So it works out. And again, for the 4th partial sum, it's kind of more trouble than it's worth than it was to add them. But for the next partial sum, it's going to be lovely. So let me finish this one out. So this is 2 take away. And then Desmos, oh beautiful Desmos, tells us that this is 15/8, which means I am back where I started. It's 1/8 or 0.125. So I proved that this formula right here works for the partial sum here, right? That formula is getting us this bit right here, which gets us this bit right here. And that takes the place of us having to write them all out and add them ourselves, right? This right here is S4 also. And again, for this particular one, whatever. The formula's a little bit more tedious perhaps than we need. But for this next one, let's do this. So this is the whole thing from 0 to infinity of 1/2 to the n, take away, and then I don't want to write all these out. Geez Louise. So it's S sub 10. I want to take away the first 10 terms, which will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So if you think about this one, the 4 was from n equals 0 through 3, right? 0, 1, 2, 3. 0, 1, 2, 3. That's 4 terms. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is going to be from n equals 0 through 9 that you're taking away, and that's going to leave 10 through infinity left over. All right, so this, again, we still know that that is, by part A, we already proved it, it's 2. Minus, and I don't want to write all these out. There's like a whole bunch of them. I couldn't fit them on a paper. But what I could fit is the formula. It's 1 times, so A was 1 minus R. Real quick, just a reminder, A is 1, R is 1/2 for this whole page. Right, so it's 1 times 1 minus over 1 minus. But this one's going to be to the 10 power, right, over 1 minus 1/2. And we are totally going to have Desmos do that for us. We are not going to type that. Okay, so I'm going to go back to Desmos. And heck, I'm going to copy and paste because what changed is this value right here. Oop, but it's still to a power, sorry. So 10. And then if I want a fraction, there I have it. So decimal fraction, just like that. Okay, so that would be 2 take away 1023 over 512. Let me go back. That would be 2 take away, and then from Desmos we get 1023. I can make that a 3 over 512. Desmos. We're not going to find that by hand. There's no point. So that would be 1024 minus 1023, which would be 1 over 512. A decimal approximation would be 0.001953. Right, it would go on. I shouldn't put the dot, dot, dot. I'll just let it go. So this is key. So we've learned in this page that we can take the basic formula for a geometric series that starts at 0 always and modify it as we need to. Simple modifications, you can kind of do it by hand, no problem. But more complicated ones, you wouldn't want to do this by hand. You can use this formula to find that partial sum and then take it away from the original, from n equals 0 to infinity sum, and you can find your result.